right, this is chapter 12 on weathering, erosion, and soil resources. So, soil is essentially rock that has been weathered down to very fine particles. But the difference between soil and like alluvium is that soil contains a lot of organic matter, and it's something that can support plant growth, where you're just broken down like alluvium, broken down rock like alluvium or beach sand really can't support plant growth. So it's an unconsolidated material overlying bedrock, materials of supporting plant growth. Regolith encompasses all unconsolidated material at the surface, fertile or not. So this would be if it's anything broken down. Soil is produced by weathering, which involves chemical, physical, and biological processes to break down rocks. This is dependent on climate, topography, the original rock that's being broken down, and time. So, mechanical weathering, this is things like water breaking it down into smaller pieces, frost wedging, which is when water gets into the cracks in rocks. And when it freezes in the winter, then ice expands when it freezes, so it just breaks that up more and more and more. Salt can do the same thing. Salty water gets in there, and then when it dries up, then the salt precipitates out, and then it can kind of split up rock as well. So we see this in very cold and in very arid regions. I think that's it here. Here's an image showing how chemical weathering increases surface area. So weathering in general, mechanical or chemical, kind of starts tearing at the edges and the corners first. Um, so the smaller the piece, the faster it's going to weather. And while this is true for mechanical, it's especially true for chemical weathering. And so once you get things like frost wedging happening and breaking a large boulder or cliff face up into smaller pieces, your chemical weathering gets in there around the smaller rocks or grains or whatever it may be, and can really kind of start eating at it much quicker. So once it starts breaking up, you start accelerating the rate of weathering. We said cold or arid, so obviously climate and the amount of water have a major factor in the rate of weathering as well as the type of weathering that occurs. And you get chemical weathering with water. While water can mechanically break it up, it also can dissolve a lot of rocks, like the salts, like halite, as well as limestone dissolves easily. That's how we get our caves and karst features here in Kentucky. And warm climates are also more conducive to chemical weathering because warm water dissolves faster or more effectively than cold water does. Chemical weathering is the breakdown of minerals by a chemical reaction with water and the other chemicals dissolved in water or with gases in the air. So if you think of like our karst with the limestone dissolving, it dissolves so much faster if you get a little bit of acid rain in there. So the higher, or wait, hold on, let me think. Acid is lower pH. So the lower pH, the more acidic the water is, the faster that limestone is going to dissolve, which is where then the CO2 actually promotes um, acid rain, which then helps dissolve the limestone bedrock a lot faster. Calcite, also like limestone, pretty much made out of the same stuff, is prone to dissolution. Calcite is like a mineral in limestone. It's acceptable to acid. Yes, I just said that. Silicates are less susceptible to chemical weathering. They just don't really dissolve as easily. And then some examples here are feldspars would be silicates. Quartz is a silicate. Iron oxides and hydroxides don't dissolve as easily. So then now we're going to kind of switch gears from weathering into soil profile. So if you dig a hole in the ground, you're going to generally find this. Now, there are places where some of these soil horizons will be absent. And if you're in the desert, you're really not going to have much of this top. You're going to go straight to more of the bedrock. Some areas the soil is just too thin, or if it's been eroded away, maybe this is gone and you'll kind of get this. But anyways, it starts as bedrock and it starts eroding and breaking down, and it kind of does it at the surface and works its way down. So this is kind of like the first step, and then it turns into this, and then this layer turns into this layer, and then deeper, then starts looking like C, and so forth until you get this full soil profile. The top is O for organic. That's where you get a lot of the organic material. A is usually still kind of organic, but starting to get more into grains. And it's leached. So water comes in, rains, it'll pick up some of these like little pieces, salts or little pieces of limestone or whatever, but it'll anything that can dissolve, it'll leach that out of the soil. Um, and then it deposits, it's here in the E layer, where then you get wait, no, hold on. In the B layer, the zone of accumulation, where you'll get it's deposited and it precipitates out of solution here. Um, and the C layer is practically like broken pieces of bedrock. It really doesn't even look like soil anymore. So let's see, the organic, zone of leaching, zone of accumulation, and then the weathered parent material. The figure explains it so much better than all the words over here. Here are some images of that. And so you can see like this one here, a very, very thick organic layer. Um, this one here, not so much. So it just depends on the bedrock and the climate as to how much uh, of each profile layer you're going to get. You find more organics in more temperate climates where you just have more organic material. Soil classification. So in geology, we use a lot of these triangle charts. And I don't know if we've covered this or not, but how you read this is you look at the percentages here. So this is the percentage of sand. So let's say you have soil and it has 70% sand. And let's say it has 30% clay. You'd be right here at this sandy clay low. Um, Now, what if it also had a little bit of silt in it? Then you can come up and it might be a silty clay loam instead of a sandy clay loam. So you follow it down. If it has 30% silt, um, and that's it, you would still call it a clay because most of the material would be clay here. It would be 70% clay, yeah, 70% clay, 30% silt, and effectively um, not enough sand here to bring it down. Hold on, let me think this through. Yes, yeah, this is 100% clay. Sorry, I confused myself for a second. So 100% clay coming down, you got 30%, you're still in a clay. Um, so loams are pretty much right in the middle, and they have almost equal parts of everything. Um, and they tend to form PEDs, which are clumps of soils. PED forming soils resist erosion, where finer soils may become loess. Um, Loess is a wind-blown deposit, and it's very fragile, if you will. It's very susceptible to failure. Um, So soil classification, we have pedalfers, which are moderately leached soil rich in residual iron and aluminum oxides, and you find those in your humid climates. And we have pedicals, which are calcium carbonate um, and bearing, and you find those in dry climates because you don't have the water to dissolve the calcium carbonate out. All right, and that is that for yes. All right, so we will start talking about soils and human activities next, but I'm going to go ahead and say laterite is a extreme variety of a pedal-fir soil. In fact, this word I don't really hear it used all that often. But laterite you do hear used, and it forms in tropical climates, so extremely humid, and it has practically no soluble nutrients left. And it's pretty much just like a really great deposit of iron oxides because everything else has kind of been washed away, leaving a whole lot of irons. Um, and so when we find this from past soils, this is a source that people will mine very frequently and look for those for iron mining. All right, and so then next we will talk about soils and people.